Okay, so I'm starting the Zoom session a little early today to go over a prior homework, the first homework on rejection criteria. That's Module 15, Topic 2, Homework 1. This was actually due a few days ago. There was a lecture video about it, and there was also a homework preview where I just made up another problem. This is kind of a recap, but there were a couple of mistakes that I saw frequently on the homework when I was grading it. And so I just want to go through it, with this specific homework question to try to straighten that out. So it's about the fuel efficiency data that we have. So over in our data spreadsheets, here's the automobile fuel efficiency. You've seen this in some other exercises that referred to the same data. And so this is a hypothesis testing question. The EPA, Environmental Protection Agency, claims that the emissions are normally distributed with a mean of 1.45 grams per mile and a standard deviation of 0.4 grams per mile. And they claim that the emissions are normally distributed. And we collect data to attack the null hypothesis to see if we can reject it in favor of an alternative. The alternative this time is that the mean is less than 1.4 grams per mile. So I'm going to start by drawing a couple of pictures here, the distribution curves, because it's really important to have the picture in mind as you go through the logic. So I'm going to draw two curves. We're going to draw the distribution of X, the efficiency, if the null hypothesis is true. Okay. And so their hypothesis is that this X is normally distributed and that the mean right here in the middle is 1.45 grams per mile, and that 1 STD, the standard deviation of X, this distance here, let me make that picture a little bigger. That distance is the 0.4 grams per mile. Okay. So like one standard deviation, or 0.4 grams above the mean, would be 1.85 grams per mile. Okay. So on the distribution curve for X, if you don't want to do grams per mile, you could do standardized units. The 1.85 grams per mile would be 1 STD above the mean. It's just changing the scale on the axis. Now, but what's going to be more relevant to what we're doing is the distribution of the sample mean. If the null hypothesis is true. So the middle will still be here at 1.45 grams per mile. Okay. We're going to keep the same mean, but the standard deviation of x bar n, that's the standard deviation of x divided by the square root of n. So that's 0.4 over the square root of however many cars we have in our sample. Okay. Now, I need to know how many cars are there going to be in the sample, just to make the picture real detailed right now. You don't need this until later in the story, but I want to scroll down here. The sample size that we're talking about here is 28. They're going to get a sample 28 different cars. I don't know if you can see that, but in the homework here, that subscript is the sample size, so it'll be 28. Okay. So I'll just go ahead and get that number, get my calculator out here, and let's see, I'll do 0.4 divided by, oh, no, that's not what I want. Hang on. Divided by, and then I'll make my parentheses, and I'll say 28. Do the square root of the 28. And close the parentheses. Okay, so I get 0.076 grams per mile. Okay, now, my point is that the standard deviation is smaller. This is going to be a pointier curve, narrower and taller than the distribution of x. And so it's this distance here that's the small number, the 0.076. Okay. Now that we've got the picture, let's go through these questions. So if we're going to go out and get a sample, okay, we get some data. Not all the car models, not all the cars, just 28 randomly selected cars. But if the mean of that is a lot less than 1.45 miles per gallon, that's when we will reject the null hypothesis. So, which word or phrase belongs in the blank? We'll reject the null hypothesis if the sample mean is significantly less than 1.45 miles per gallon. So if the sample mean, if the x bar comes down far on that side, on the left tail, then we'll reject the null hypothesis. So question C is asking, if we're going to reject the null hypothesis at the 1% significance level, where's the rejection zone? So it'd come way over here. And the rejection zone is the lowest 1% of all the sample means. Okay. So the idea is that we know how the sample mean is distributed because of the central limit theorem. If x is normal, then so is x bar. Samples, we need x to be normal in this example because the sample size is a little bit small. Okay. So we know how if all the possible samples that you could take produce different sample means, and this is how those sample means are all distributed, and the bottom 1% of them fall here in this corner, and that's where we would reject the null hypothesis. So it's on the left-hand end because it's a left-sided alternative, and it's the area's 1% because alpha is 0.01. All right, so we've drawn the rejection zone. And now, if the sample mean falls inside the rejection zone, so in question D here, if the sample mean is inside the rejection zone, where is it? It would be in this shaded part, this bottom 1%. Then the area to the left of the sample mean, is that going to be more or less than 1%? Well, the whole black shaded area here is 1%. The area to the left of the sample mean is going to be less than that. Okay. But question E, if the sample mean falls exactly on the edge of the rejection zone, exactly right here, question E, sample mean falls exactly on the edge of the rejection zone, then the area to the left of it will be exactly 1%. So, going back to question E over here, the area to the left of this point is equal to 1%. Now here's where lots of people had the wrong answer, and they all had the same wrong answer, and I don't know what was happening. First off, this first set of instructions here is if you're using the TI-84 calculator. If you don't have one of those, you could come down here, and this is how you do it using Excel. So I want to type this in Excel because I don't know what was going wrong, but let's make the Excel display a little bigger here. I want to say I type the equals to make a formula, and the function over here in the workbook, it says norm.env, so I'll type that. and then 0.01, 1.45, 0.4 over, and I look right up here at that subscript, 28 right here, and that's what I type in, the square root 28. And so I get 1.27 grams per mile. Now, these, I can show lots of digits on these. This is not dependent on data. There's no uncertain numbers here. These are perfect numbers. So I can keep as many digits as I want. Okay. Or I could do the same thing in standardized units. So up here, you see the numbers that I plugged in here, the 1.45, that was grams per mile, and the 0.4, that was grams per mile. So the answer that comes out is going to also be in grams per mile. But down here, I'm just using the STDs as the units. So, the mean is 0 STDs, and the standard deviation, is 1 STD. So, all right. So to get the number in Excel, I'll just type equals norm.s.inv. That left tail area, the alpha, is the 0.01. Close the parentheses, and I get about negative 2.33 STDs. All right, so that's question F. So this was grams per mile. And this one is STDs. I use the norm.inv functions, either plugging in the real mean and standard deviation, or using the standard normal and getting the answer in standard units. Okay. Now, we just want, it ought to be that if we convert from standardized units into natural units, we should get the same thing. So if we were to take this many STDs and convert it into grams per mile, we should get the 1.27. So I need to convert negative 2 point, it's roughly 33. Ooh, that's a little rounding error there. Okay, well, I'm going to keep all my digits. So let's do 326. Okay. So we're this many STDs below the mean. So we're going to take the mean. And we're going to subtract 2.326 standard deviations. And what's the standard deviation of this curve? It's this 0.076 grams per mile. So one standard deviation is this 0.4 over root 28. This whole thing is the standard deviation of x bar, critical value of x bar. So, we'll see with x bar. So I took my critical value of z and I multiplied it by the standard deviation of x bar, and I got the critical value of x bar. Okay. So now let me just do the arithmetic over here in Excel. So I'll take my 1.45 minus 2.326. Well, you know what? Instead of typing all that, I'm just going to click here, and then I get all the digits. Okay. So I'll start my formula, and I'll come over here. I'll just click on that, and then say times 0.4 over square root of 28. Okay, so let's see. Did I get back to the same place? Because if I didn't, there is some kind of mistake. Oh, there is. So I used the negative number and then I subtracted. Oh. So there you go. You get the same thing you had before. So we had 1.27 grams per mile, and our Excel input was, we did equals 1.45 minus 2.326 times 0.4 over square root of 28. So that's the answer to that question. And you can convert back in the other direction. You can convert the grams per mile into STDs. So you do the 1.27 minus the 1.45 divided by the 0.4 over square root 28. And we should get the same thing if we keep all the digits. So you keep a lot of extra digits in your cell calculation, or just click on the cell to keep them all. Then you can round off when you come back up here to the end. You get 2.33 STDs. So there's the picture. And then 1.21 grams per mile. You see the edge of the rejection zone here is where you can see this. The edge of the rejection zone is 1.27 grams per mile. So if the sample mean was 1.21 grams per mile, that's smaller, that's to the left of the critical value. So what the edge here, where I'm gesturing in the, I don't know if you can see in the picture over here, but the edge of the red shaded zone is 1.27, and our sample mean fell to the left of that inside the red shaded zone. So we reject the null hypothesis. All right. I'm going to stop this recording, and then we'll do another one starting at 11:10.